everyone sitting. I'll just go ahead and introduce myself. My name is Brett Cannon. I've been a core developer on Python for a decade come next month, which scares the crap out of me. If you want to follow me on any of the social network stuff, I'm on Twitter, I'm on G+. You can just go to about.me/Brett Cannon to get the proper names, so I don't have to fill my slide with those. So this talk, Python 3.3, why I consider it better than Python 2.7. I'm obviously biased. Having been a core developer for a long time, I played a role in trying to make Python 3 come to fruition and shape it as it is. So I'm just being upfront. I do have my biases, but other people do agree with me, so this is not just some crazy man up here. My hope is by the end of this talk, if you already know Python 3, but don't know all the details of Python 3.3, you'll at least know what was added in that version. If you don't know anything about Python 3, you'll at least have an idea of what you will get when you upgrade. And if you're still on 2.7 just here to heckle, I am happy to take the heckling and just say you're wrong. But hopefully I'll change your mind by the end. But if not, that's fine. Everyone's up to their opinion. This is divided into two parts. One is the feature set, and then one is a performance discussion. And I'm hoping to leave about 10 minutes for questions if I'm lucky. So I'm going to try to get through this so that everyone can get their questions answered. So without further ado, the feature set. So we're going to go all the way from Python 3.0 through 3.3, through at least the key points. There is some stuff, though, that if you're on 2.7 or even possibly 2.6, you can use today that have become the standard in Python 3. Some things require a feature statement to use. For instance, absolute imports, which make it so that you don't accidentally import the string module in your local directory when you actually want the string module from the standard library. Unicode literals, so that every string literal you have is automatically assumed to be Unicode. New division, such as if you 3 divided by 2 leads to 1.5 and not 1. The print function instead of statement, which I know trips everyone up because we all got muscle memory to not have parentheses, but trust me, it's better. You also get set literals, which is nice. You get set and dict comprehensions in 2.7, which do exactly what you think. We have multiple context managers, which basically means you don't necessarily need the contextlib.nested function anymore. The I/O library in 2.7 got completely rewritten in C, so it's a lot faster. That was a big change between 3.0 and 3.1, by the way. Memory views came into existence, and in Python 3.3, they actually got heavily rewritten. So if you looked at those before 3.3, you might want to have another look. There's a module called future built-ins, which gives you built-ins the way they are in Python 3. So for instance, map returns an iterator instead of a list. So you get that nice lazy evaluation. You don't blow all your memory if you have a massive list. Exceptions, the syntax got a little cleaned up. So now it's accept exception as exe or whatever variable you choose instead of a comma. So it's just a little cleaner to read. Stir.format came into being in 2.6. And in 2.7 and Python 3, we have auto numbering in the fields. And just one key little point on this, PyPy actually makes stir.format run faster than the modular string interpolation. So don't think it's necessarily going to be slower to do it that way than the old way, just so you know, because I hear that complaint sometimes. And we also added the numbers module, which helps give a proper classification of numbers, such as integers to floats to imaginary to all that stuff. If you're a more mathematician, scientific person, you probably care a lot more about that than I do, but people like it. So that's what you can already get in 2.6 and 2.7. In terms of minor features that are exclusive to Python 3, we have dict views. So basically, when you call items, keys, values, you actually get back an object that has a view back on the dictionary. So there's some space savings, and you don't have to worry about mutations underneath you. Comparison between disparate types is now a type error, so you can't accidentally compare between an int and a string and actually get a true-false. You will get an exception, so you don't make that error anymore. The old way of doing exceptions by raising with a comma for the argument is now a no-no, so we cleaned up the syntax for exceptions that way. Metaclasses became a little easier to work with. There's now a metaclass argument keyword that you can now use to specify instead of the under metaclass setting for that object. The under prepare attribute came about, which basically allows you to use an ordered dict for the creation of your object to actually keep track of the declaration order of things in a class if you want. The standard library cleanup, which I led, occurred, so a lot of modules now have much more reasonable names, and things are much more structured into packages, so it's a little easier to navigate. Logging now uses dictionaries for configuration, which is a little easier to read. The WSGI spec got a little update to be a little more clear. Super no longer requires arguments. Yes. My new favorite quote for this is Jacob Kaplan-Mauss says every time he uses this, he gets irrationally excited. It is very handy. We unified integers, so there's no longer an int long distinction. It's all just long under the hood, and we just call it int. And you no longer define the next method as just the name next when you're dealing with generators and iterators and such. It's just under next, so it matches the overall format of all other kind of magic method names. And there's now a next built in. In terms of those things that we added that are just specific to Python 3.3, the IO and OS exception hierarchy was completely reworked. So now there's a not found file error exception. So no longer do you have to catch IO error and check that error no attribute. You can actually catch a specific exception. So it's a lot easier to read and no longer those one little liners to try to do with if check and pass or raise, blah, blah. That's all gone. It's very nice. Modules, we added the LZMA module, which does the XZ compression format. We added the IP address module, which does IPv4 and IPv6 address parsing. The fault handler module helps you deal with interrupts. The email package got completely rewritten for headers, so now it's a little more sane and completely Unicode aware and usable. Dictionaries now share their keys, which in object-oriented code is a big deal because remember, every object in Python has an under dict, which manages the object namespace, right? So if you're creating a billion objects that all have an attribute named blah, this now means there's only one blah being used between those billion objects instead of a billion uses of blah. So there can be big 10 to 20% memory savings without any performance loss. Okay, so those are the simple, quickie, you guys can concept from a bullet point, get. Now we're going to get some more fancy stuff that needs a little more explanation. So to start, non-local. If you've used any scoped closures before, you may have noticed it's a little hard to try to mutate attributes. I mean, the old trick used to be, here's a list that has a single object in it. I will reference it and then mutate that single index value in the list, kind of like the old trick to having mutatable default argument to functions or methods. Well, when we added non-local, that did away with that. So now you can declare a variable as either global or non-local, and this way you can make sure you can actually mutate objects at the correct scope level that you care about. So in this example, for instance, by declaring higher scoped as non-local, that variable, the top level function, can actually be mutated in the closure and properly do what you would expect. So basically, closures are no longer read-only for the captured variables. It's now read or write. Extended iterable unpacking. This is a nice little handy thing. Basically, when you do variable assignment, you can now use an asterisk to mark that something is supposed to collect all the extra arguments out of an iterable, and basically everything else gets unpacked. So in the first example, first comma star rest equals range 5. As you can see, first gets 0, and all the rest of what's supposed to come out of that iterable gets set to rest. Now the really cool thing is you can actually put this in the middle of a list, or not a list, but sequence of variable names, so that you can actually pack specific amounts on either side of the sequence and have everything else kind of like get packed up in the middle if you want. So as you can see here, the B variable in the middle is actually what gets the variable amount of values in the list, while A and C specifically only get one value. A big thing for you extension developers, we defined a stable ABI in Python 3. Basically, quoting from, I think the PEP, I don't remember where I got these quotes. Basically, we define a stable set of APIs at the C level. And basically, we guarantee those will be available for the rest of the lifetime of Python 3. So what this means is if you develop your C extensions to the stable ABI, you don't have to necessarily recompile for every single version of Python because something at the ABI level changed, right? It's going to be stable. You don't have to worry about it. It will always just work. You don't have to do updates on every single version. I'll talk about a new feature in the few slides later that'll show that you don't even have to recompile ever for anything. You can do it just once if you do it right, and it'll just keep working for Python 3. Concurrent.futures, this is kind of a cool little thing that we got into the standard library. For any of you who want really dead simple ways to take embarrassingly parallel work and just shove it off to threads or processes, you can do it really easily. So if you look at this example, it takes 6 seconds to calculate numbers 0 to 19 to the power of a million. But if you basically just add an import line, a context manager that uses processes, and change one map call to an executor.map, it all happens in a second. And that's all it takes to use as many processes as you need to do this calculation in parallel. It's really nice, really simple, and as I said, for those embarrassingly parallel workloads, this is great, and it's almost just a drop-in replacement for where you would have just used math to do something. Decimal got completely re-implemented in C in Python 3.3. Those numbers are not typos. Literally, things using decimal are now oftentimes 30 times, not percent, 30 times faster. And we've actually seen numbers as high as 80 times faster. So if you do any work with the decimal module, you seriously should look at using Python 3.3. Your workloads will be significantly faster. It's ridiculous. OK, qualified names. We cleaned up the way things are now named, such that on an object, if you look at the under qual name, it now includes for methods the name of the class as well as the method. So if you use under name, which is scoped from the global namespace for the module, and tack that onto under qual name, you can now get the fully qualified name in your overall namespace of where something came from, right? So in this example, class C defines the method f. As you can see, the old under name on the method f was just f, but the qual name is actually c.f. And if the module name was foo, and just tack that on, you could have said foo.c.f with that little snippet of code up there. So no more wondering, what f is this? I don't know. Just use qual name instead, and you can actually figure it out. Yield from. You will care about this thanks to Guido, which I'm sure he will talk about on Sunday. But basically, it's a new thing in Python 3.3. It makes it really easy to factor out generators. So I'll go over the example real quick, and it'll be a little more obvious. Let's say you literally had a function that did nothing more than just yielded 3 times, right? How would you factor out those last 2 yields cleanly before yield from? You'd probably factor it out to another generator, right? And then you'd have a for loop. We would just go for x in the generator, yield whatever, right? So you'd stick in this for loop to try to just constantly yield and pass it up. Well, that's now gone with yield from. It's a single keyword that does the yielding straight up. Now, it's fancier than just a for loop, though. You have to realize that the way this works is it will send everything all the way down the stack to the end, so that let's say you have stacked yield froms and you do a send on your generator, that will fall through all the yield frames all the way down to the bottom. So you don't have to, so it's a little fancier than just a for loop. You can think of it that way in terms of refactoring of generators out into separate generators, but do realize there's a little bit more behind it than just syntactic sugar for a for loop. So it's really handy though, and it's going to come into play in Python 3.4 because Guido's been working on an async event loop system, and it completely runs off of yield from. And he's completely tied it into yield from because he likes that way of doing async. So this will become a key thing in the future of Python in terms of asynchronous workloads. Venv, so this is new in Python 3.3. We've essentially just added virtual env to Python. Yes, it's a good thing. So as I said, it's basically virtual env. It's just built in. You can either use the venv modules with the -m to create a new virtual environment, or we now include a pyvenv script that'll do the exact same thing. Because it's now directly integrated into Python, a lot of the edge cases you might be used to hitting with virtual env is now gone because it's a directly supported thing. And an environment now can be nothing more than a copy of the binary or even just a symlink on the right OS, a little config file, and a sites-packages directory. And that's it. It's really lightweight, and Python now completely supports it all the way through, and it's fantastic. No more downloading virtual env every single project. It's just there. I love it. OK. So those are things that needed a slide. Now these are things that needs lots of slides. This is more thematic, but still need to cover them. So exceptions. We did a lot of work in trying to make sure exceptions were a little cleaned up in terms of syntax and how they worked. now everything kind of tied together. So first thing, we now include the traceback with the exception. So you might be used to having to look into the sys module to find what the current traceback was, or playing with the traceback module and all that stuff. Well, it's not necessarily required anymore. You can use the traceback module to do clean printing of stuff, but to actually get to the traceback of the current exception, it's just there as under traceback. So no more having to dig it out or anywhere. It's just carried along with the exception. We also added exception chaining, both implicit and explicit. So with implicit exception chaining, let's say you've raised an exception, you catch that active exception, and then you raise another one. Well, what happens is we set this attribute called under context on the new raise exception, which contains the previous exception. So that way, there's no loss of data at all. If you forgot to specify that, oh, this exception triggered this other exception or whatever, you don't need to. It's all completely implicit. And we will say, during the handling of the above exception, another exception happened to occur. So there's no loss of actual traceback data when you raise an exception, whether you explicitly wanted to or not. So it really makes exceptions a lot cleaner and easier to work with because there's just no loss of data anymore in terms of what you need for debugging. But let's say you want to be very explicit about this and really say, okay, this exception really, really did happen because of this other exception, not just, oh, I caught an attribute error and I want to raise a value error. It's like, all right, this value error specifically happened because of this attribute error. Well, we now have a under clause attribute. And in Python 3.3, you can suppress it with adding the from none. But basically, the syntax is raise exception from the other exception. And it's much like implicit exception chaining, except the wording's a little different and the attribute's different. So here, as we say, the above exception was the direct cause of the following exception. So as I said, one is implicit, where you just do a raise, and we kind of just implicitly say, OK, this happened, and then this happened, so they're probably connected. And this one is you explicitly state for the user, this happened because of this. Once again, it's very nice because there's no more loss of any exception information if you're struggling between multiple exceptions chaining along. Import. So part of this is my fault. So import lib, for those of you that don't know, I rewrote import in pure Python and made the import lib library. Added that in Python 3.1, 2, somewhere around there. But what happened in Python 3.3, it is now the actual implementation for import. So all that C code is now gone. It's all actually implemented in Python itself. The big deal about this is the goal is that all the VMs will be now using the exact same implementation of import. For any of you who have ever had to deal with a weird import problem because of the different VMs, it should hopefully go all away in Python 3.3 once they all support it. It's also easier to customize and blah, blah, blah. I got a talk on Sunday about how import works, and I'll cover all this. But basically, if you do any fancy import stuff, this will make your lives a lot easier. We also tweaked the import lock, which any of you who've had deadlock in threads doing imports and whatever, you should be very happy now. Basically what happened is in Python 3.3, we added a fine-grained import lock per module instead of per process. So what this means is, previously, if you did an import that triggered a thread as a side effect, and then in that thread it did its own import, that would deadlock the interpreter. This could happen if, for instance, you imported a module, it launched a thread, and this thread called some code that in the function itself actually did an import, and this can happen like in the OS module. Some of the functions in the OS module actually import things as a side effect of being called for startup reasons. This does away with that problem. So you will no longer get that deadlock. Excuse me. The other side effect and perk of this is threads now block until they complete. So if you have circular import problems, it can possibly help because it'll allow modules to not be fully initialized to continue the import. So as long as your dependencies don't fall in a certain way, you have at least a chance for a circular import dependency to actually continue on and actually finish and actually succeed. It doesn't solve it completely. You might still have to restructure ordering and stuff to make circular imports work, but at least it can help. But the key thing is no more deadlocks in import. The other thing in Python 3, I believe this went in 3.1 or 2, I can't remember, is the under PyCache directory. So I'm sure all of us are used to Python 2, where we end up with a directory that has a bunch of nice clean .py files, and suddenly we run our code, and suddenly we've doubled the number of files we have to .pyc. And then, oh, let's run with -o, and now we've added another set. So now we've got 3 times as many files in a directory. I hate it. I'm sure you all hate it. It's not a problem anymore. So in Python 3, what happens is all those files get dumped into a directory called /pycache. Now, the really nice thing about this is every single .pyc file now has a suffix of the interpreter and the version used for Python. So what this means is for instance, if your code runs on Python 3, Python 2, Python bazillion and a half, it will all go in the same directory and they won't overwrite each other, right? So you no longer have to worry about other versions of Python running on that code and overwriting that PYC file and having to regenerate every single time because you're running your tests or whatever and having to take that overhead. The other nice thing is if you test against multiple VMs or something, VMs can also write their own version of a .pyc file and then take advantage of that. And then once again, it won't overwrite anyone else's code. You can still distribute only .pyc without the source if you want to. This does not take that away. I'm going to say unfortunately, but I am biased and I really don't like that, but to each their own. But you can still do that, and we did not take that away. It just really keeps, it's really nice to have just, when you import all the code, just have a new directory, and then all your .pyc files, all your .py files are just there, and just the directory, as I said, instead of tripling the number of files potentially. It makes it a lot easier to work with. A biggie that at least the Linux vendors have really been wanting are namespace packages. This is new in Python 3.3. Basically, if you have a directory that does not have an init file to define a package, but the directory name matches, what'll happen is that'll get collected as a possible entry in a namespace package. And then the search will continue through sys.path and what have you, and it'll just keep collecting directories that have that name, as long as there's no init file. And at the end, if no specific file has been found, whether it's a named module or a package with an init, all those directories will get packaged up. That'll get set as the path on a module, and you'll now have a namespace package. So the common example is, let's say you have Zope, and you've got 3 different packages in 3 different directories. Well, if you have them on 3 different directories, but they all have a Zope directory at the top right off of sys.path, those 3 directories will all get packaged up, and they'll all become a single Zope package. So it'll allow you to actually distribute your projects as separate things as long as they all have the same top-level directory. So you could divvy it up and ship 3, 4, 5, whatever packages. Everyone can install them individually as long as that key top directory has no init, but that's what gets put on the sys.path. Python 3.3 will collect them all up and treat them as a single package. Yeah, it's a very, very nice feature. And the other nice thing is if anything changes above it, so sys.path or the path of a higher level package directory or package, it'll actually be recalculated on the fly. So you don't have to worry about if you suddenly add another entry into the parent package, whether it's sys.path or higher up in the package, having that not get picked up and carried down through the packages itself. It'll actually recalculate and dynamically start using it. Functions. Functions also got a nice bunch of updates in Python 3. One really fantastic thing I use constantly, and I'm so glad we added, were keyword-only arguments. So if you add an asterisk and nothing else, and add things afterwards, or like star args and then a comma and then some arguments, those become keyword-only arguments, which means you can only call them when you use their name in the function call. This is fantastic for expanding pre-existing APIs. Because the old way of, let's say, I take 3 arguments like bacon spam, and then you want to add a different argument. If you just tacked on different, in the old way, you could potentially call the function with 3 arguments by accident and not realize you're suddenly turning some functionality on the new API because you suddenly set different. You can't do that accidentally anymore. You have to now say in a function call, different equals true or false or for or whatever you want. But you have to explicitly add it now. So if you expand an API now, you can just say, all right, if you want to turn on this new functionality, you have to explicitly use a named argument, no longer accidentally overflowing into some new argument by accident. Function annotations. This basically allows you to take any parameter in a function and return value and kind of add an object that acts as an annotation for that function. Lots of people think of this as a way of adding type annotations for functions, which you can do, but it's not explicitly meant for that. It's just a way to annotate things in any way possible. It could be documentation, it can be a type, it could be whatever you want. And actually, the standard library explicitly does not use function annotations so that the community can decide however they want, and they don't feel like you're being boxed in saying you have to use it for types or you have to use it for docs or whatever. I actually put in code myself that used specified types, and Raven Hedger took it right out, saying you're not supposed to do that, naughty Brett. So you do whatever you want with them, but they're kind of handy, and it's kind of a neat way to do documentation. Signature objects. This is my fault, somewhat. So these are new in Python 3.3. Basically, it's an object representation of callables. So any of you have ever used the inspect module and used like get full argspec, I think is the function name, to try to query an object callable to find out what are the arguments, how many there are, et cetera, et cetera. It gives you a bunch of lists and tuples and stuff, and it's not really easy to work with. This gives you an actual object to query. It's telling you, all right, here are the number of positional arguments, here are the number of keyword-only arguments, here are the default arguments, here are the annotations, et cetera, et cetera, et cetera. It's much easier to work with. It obviously only works with Python code, although if Larry Hastings or another proposal gets into Python 3.4, we might actually be able to automatically generate this for C code. And so this would make it really easy to query objects to figure out how would things bind, how many arguments does this require, and do a lot of dynamic call building. Unicode, Unicode, Unicode. As I'm sure you all know, the big controversy in Python 3 was we made everything work with Unicode because we all love the world and we don't want to be exclusive to ASCII. But basically, Unicode now pervades Python at every level you can think of. Unicode now exists while you code. ASCII is no longer the default codec for code, is now UTF-8. And for those of you that are not coding in language that can actually be represented by ASCII or such, you can now use non-ASCII identifiers. So you can now code in not all of Unicode, but a good chunk of it. You'll have to read the PEP to know the exact things because I'm not a Unicode expert. So it's not all of BMP, but it's a good subset. And chances are you can write in your native language now using identifiers that way. We now obviously have multiple ways for you to specify Unicode as string literals. In Python 3.3, we actually added back in support for the U prefix. Yeah. No, you can clap. We did this to make it easier to port code mainly. So the idea is if you already have Python code in 2.6, 2.7, or whatever, what you can do is prefix all your strings with U and then all your byte strings with B. And now once you've got that all straightened out, it can also run right through to Python 3.3 and the meaning won't change. The other thing is some people really worry about this for performance. So there's now kind of, because of this 3 concepts of strings, there's a native string which has no label on it. So in Python 2.7, it'll be the str type, and in Python 3.3, it's the str type. So it's just whatever the native str type is. You should only use that, though, if you can guarantee 100% and swear on your own children's, mother's, grandparents' lives that it stays ASCII, and then you're OK. Otherwise, you're going to shoot yourself in the foot. And I'm serious, being really, don't just assume this is how people get shot in the foot when they try to port code. If you can guarantee it'll say ASCII, you can leave off the label. If not, you should use the U prefix. If you're only targeting 3.3 and later, you can do that, and your 2.7 code, at least in terms of string literals, will just go ahead and work between 2.7 and 3.3. And obviously the B prefix for getting your bytes literal. And then, of course, there's always the under future import Unicode literals if you don't want to worry about that and just assume all non-B prefix strings are Unicode. As I said, this is the biggest hurdle people tend to run into if you've been a little sloppy with what's bytes versus strings. If you haven't been, it's really not that hard. I know that's kind of the rumor out on the internet. But the internet's wrong, which we all know happens. As long as you've been very clear about delineating what is strings and what are bytes, it's not a big thing. But if you're not worried about that because you could get away with it, that will bite you in the bum. But just be clear in your APIs and what is what, and you'll be fine. And you get better Unicode use during execution of Python. We now internally store strings as either Latin 1, UTF-16, or UTF-32. And what this means is no more narrow versus wide builds. Yes, exactly. The extension developers know what I'm talking about. So you only need one build, and it'll cover any Unicode character. Add with that the stable ABI. You can now do one compile for Python 3, and for, at least for 3.3 and farther, you only do it once per OS, and as long as nothing shifts in terms of what your needs, you don't have to recompile for every single version of Python thereafter. It's very nice. So that's a big thing. You can also save memory doing this. So when Martin von Loos did this work, he used a Django benchmark that if you use a narrow build compared to 2.7, Python 3.3 used a little less than 8% more memory. But if you use a wide build, Python 3.3 was actually smaller by over 9%. So if you're doing internationalized code where you need to care about Unicode usage, you'll probably get a lot more, you'll actually save memory if you switch to Python 3.3. So if you notice, Python 3.3 has a lot of stuff added to help you with memory usage, such as the key sharing and this. So if you've been having memory issues, Python 3.3 will help you with that. Okay, the big thing, who's faster? Obviously a big question everyone asks. So I ran my own benchmarks. Basically, I checked out the code on the same day, compiled 2.7, 3.3 right off Python's trunk. I could download the binaries, but honestly, you're going to end up running the exact same code that is, so I didn't want to do it because I'm lazy. I did use a wide build because that equals out the abilities. If you don't like that, tough. So the results are all relative between two binaries because I use the unladen swallow benchmark suite, which as part of this work, I also merged in the PyPy benchmark suite and moved as many benchmarks as I could over to Python 3. Some of the benchmarks I used aren't public in the unladen swallow benchmark suite because I use libraries that have not released Python 3 support yet, but it's in their trunk code. I believe like HTML5 lib supports it in trunk, but they haven't done a release with it. But I included it all here. So that's how I did the benchmarking for these numbers. You can reproduce if you want, but basically, if you sorted all the benchmarks and took the median, they're exactly the same. Which is fantastic, I think. Now, this actually sped up. When I did this for PyCon Argentina, Python 3.3 was 5% slower, but if you track down Thomas Wooters, he can tell you he did some experiments at Google where basically 5% you can get with just tweaking how your compiler runs easily. So it's still completely within the realm of just compiler flags. So it's a wash, basically. Now you might be saying, oh, median, who cares? You got all these other benchmarks that might not equal out. Well, I'll get to that. But to be upfront, the slowest benchmark is startup with -s. It's 73% slower. Now, this is actually faster than it was in Python 3.2. One of the perks of import lib is it caches some things in terms of stat calls and such. So it's actually startup faster than 3.2. But because Unicode now pervades everything, there's a lot more to import because we have to import encodings and all this other stuff. So it starts up slower. I'm hoping for Python 3.4 to have a look at this, but that is the slowest bit. Telco, which uses decimal, is 46.96 times faster. That's not 46%, that's 46 times. I was not kidding. The new C version of decimal is extremely fast. Here, all the benchmarks, except for the two extremes to keep the scale reasonable, sorted. And as you can see, it's close to being just split down the middle. It really just, you can choose one benchmark, and I can show you another one on the other side that's faster or slower, and it's just like, it really just is a complete wash. If you want to be picky, it's like, all right, those include micro benchmarks. What about real world stuff? Well, here are the macro benchmarks in the benchmark suite. You can have one like pathlib, which is really slow, though admittedly, it does a lot more Python 3 because of extra support in the OS module and such. So, and on OS 10 on top of it. But like Mako is real and Genshi is real. Django's there on 1.5.0, and it's only 5% slower. As I said, 5% is within compiler flags. But then HTML5 lib, 2 to 3, and Chameleon all run faster in Python 3.3 by a good amount, right? I mean, that's 12%. So really, you can argue, based on your load, it's going to be faster or slower, but either way, chances are faster or slower within spitting distance. So it really is not a big thing. And these numbers have actually improved. As I said, when I did this for PyCon Argentina, basically the exact same. It's just gotten a little faster for Python 3.3. So this is not going to get worse, it's just going to get better. So performance is really not a problem. And with that, you can stare at my cat while I take questions. Yes? I think there are mics, yeah. There's a mic there. Do we have any other mics? Is that the one mic? Okay, I'll just keep my neck craned to the right.
So, hello? Okay. How does super work without arguments? Is it magic? Like, how does it know what it's referring to?
Yeah, it's pixie dust. Basically, so the question is how does super with no arguments actually work? Technically, under the hood, basically what happens is we cache specifically what the arguments would have been in the basically the closure space of that function, and we just magically just add it. So, yes, it's kind of magic. Robert?
Now that dictionaries share keys, is that using intern under the hood? The big question is, do they disappear when the ref count drops to 0, or do they stay in the intern? No,
this is not tweak interning. So interning sticks around and all that. It's just the way the keys point to things and such, and the structs underneath are a lot smaller and a lot simpler, and just do a lot more in direction.
Okay.
If you want the real details, ask Mark Shannon. He wrote it.
Okay.
Anyone else, or did I sell Python that well? All right. Well, go ahead.
So I do have one more if no one else has one.
Yeah, go ahead.
So the yield from, supposing I wanted to yield 10 from something, like the next 10 from this generator, I normally would make a loop range 10 and yield that many times.
So you want to restrict it to only 10 when it could be potentially more?
Right.
Yeah, yield from won't help you with that case.
What's that?
Yield from will not allow you to specify that. It's yield completely until exhaustion. There's no way to specify a limit.
I have another one too.
Sure.
So one of the big no-nos in Python 3 was, I think it was Python 3, was you cannot re-raise an exception from outside of the except block. Is that something that you can now do with that under context?
I don't know. I've never done it.
Okay.
Do it. Give it a shot and let me know.
I will.
After virtual env, is there a plan to add one of the installers, pip or easy install also?
No. You can talk to Nick Coughlin, but specifically no. We have absolutely zero plans to do that. We're actually going to clean it up such that you have a dead simple installer to make it easy to get pip or build out or bento or whatever builder installer you want. And then you just go run with them. We've realized we are not the best people to manage this. It's better to let the ecosystem choose and grow and go faster than the standard lib. So no, we're not going down that road.
One quick piece came up before. Is help going to start using the new signatures soon? Because right now help ignores when you reset signatures.
It can. There's no specific reason why it can't. Someone just has to write the code.
Okay.
Yeah, patch is welcome, exactly.
Okay.
Sorry, yeah, one classic mistake I make is with using source control is I remove a directory and then I change to a different branch and I run it and it'll keep the PYC files around and I'll import a module that's the PY file is in there. PyCache will check, right, for the existence of the PY file and clear out and solve all my problems.
The PY file has to exist, and then the old PYC files will just sit there and nothing will happen to them.
Second question. Do PYC files really help? Because they're always a problem. Like
They help some. Basically, they save you the parse and the AST compilation step, and that's roughly it. So there's definitely help. I mean, it kind of depends on your situation, but yeah, no, they're definitely helpful.
With the metaclass keyword being added as a class keyword instead of double underbar metaclass, is there any way of backwards, like adding to the futures module for 2.7 so that we could actually have metaclass as a keyword there? Because I have to maintain two different code bases.
I think there's a with the 6 package. There's the 6 package project has a way to deal with metaclasses. I don't know how they get around it. I think you have to inherit from a specific class and then they do the right thing under the hood. So if you need help porting, I should mention, if you need help porting, there's going to be a porting clinic Saturday and Sunday being run by Barry Walsaw and Yarko, where you can get some help from them and some other people who have experience. They'll answer your questions, but one of the things they'll probably suggest is use the 6 project, and it has help in there to help you do a common way to do meta classes between the two. Anyone else? All right, well, I'm tall. I'm sure you can see me around the conference. Feel free to stop me and ask questions, and thanks, everyone.